This example is from the text Conceptual Dynamics. Specifically, this is example 3.4-6. The problem statement reads, a slotted bar pinned at point O rotates with an angle described by the function theta equals 5t, where theta is in radians and t is in seconds. As the bar rotates, it forces pin A to travel along the vertical guide shown. At the point when t equals 0.2 seconds, determine A, the magnitude of the velocity of pin A, and B, the magnitude of the acceleration of pin A. So as we read the problem, we try to understand what's happening. We can sort of see this figure here, and we can imagine that this bar pinned at O is rotating upwards. And as it rotates upwards, this pin is forced to move up this slot. So reading the problem, we're told how the angle theta moves. So we're told that theta as a function of t is 5t, the units of radians. And we desire to find the velocity, the magnitude of the velocity of pin A, and the magnitude of the acceleration of pin A at t equals 0.2 seconds. So at 0.2 seconds, theta equals 1 radian. So that's what we are given explicitly. Here we again have a planar motion problem. So we have a particle that's moving in 2 dimensions. In reality, it's moving in 1 dimension. It's moving in just a straight line, but we are given information that relates to more than that. So far, we've learned 2 different coordinate systems, xy or Cartesian coordinates, and nt or path coordinates, and most recently we learned a 3rd coordinate system called a polar coordinate frame. Since this particle is moving in a straight line, since its acceleration is in a straight line, we could use xy or Cartesian coordinates to solve this problem. The motion and the acceleration is entirely, for example, in the y direction, in the vertical direction. If you go through that process, you use some geometry, you can sort of set up some right triangles and things. The calculation gets a little tedious. You have to do quite a bit of differentiation and algebraic manipulation, but it's definitely doable. As an alternative, we are going to use polar coordinates. And the reason polar coordinates can be used in this case is because we are given information about how the particle is moving with respect to kind of a fixed point. In essence, an angle and a radius with respect to this fixed point. And that makes it well suited to polar coordinates. If we think back to what we've learned about polar coordinates, we have one axis, the radial axis, that points from the reference point out towards the particle. And then the second is the transverse direction. And it's perpendicular to the radial direction, and it's positive in the direction of increasing theta, which in this case is that direction. This is again a body fixed coordinate system, so as the particle moves, the reference frame will move with it and rotate with it. So having set up our coordinate system in this manner, we've learned how to express velocity and acceleration in the polar coordinate frame. Specifically, velocity is equal to r dot in the radial direction plus r theta dot in the transverse direction. And then acceleration is r double dot minus r theta dot squared in the radial direction plus r double dot plus 2r dot theta dot in the transverse direction. So looking at these two equations, there's quite a bit of information that we need. And looking at what we've been given explicitly, we haven't been given too much. But it turns out we can find a lot of what we need. So we're given theta. We can find theta dot and theta double dot quite easily. Okay, so theta as a function of time is 5t. If we differentiate that with respect to time, you get that theta dot is a constant 5 radians per second. And if we differentiate it one more time, since this is constant, theta dot is just 0. Okay. When we do these polar coordinate problems, we will always want to use radian units for our angles, not degrees. Another thing that we'll need is radius, and we can get that from geometry. So at this time, 0.2 seconds, the time we're interested in, theta is 1 radian. We know what this distance is. And so between those two, we can kind of set up a right triangle and find the magnitude of the hypotenuse, which is our radius. And since we have the opposite side and the angle in our right triangle, we can use sine to find the hypotenuse. If you think back to the mnemonic SOHCAHTOA, sine of theta is equal to opposite, which in this case is 2 meters, over hypotenuse, which is the radius we wish to find. We can solve this for r, multiply r to the left-hand side, divide through by sine, where theta is equal to 1. We punch that into our calculators, we get that the radius is approximately 2.38 meters. So that gives us another piece of information. The final piece of information that is implied in this problem is in essence the geometry, which we'll use extensively. But specifically, if you look at how this particle moves, it's constrained to move in the vertical direction. So its velocity and its acceleration will be vertical. And so with all of that, we can attempt to solve the first part of the problem. So I've rewritten all of the information that we've been given. We know that we have this equation for velocity, which I'll repeat here. Go to r dot in the radial direction plus r theta dot in the transverse direction, where our coordinate frame can be envisioned here. And so immediately, if we look at what we have r and we have theta dot. So right away, we can calculate what the transverse component of the velocity is. So v theta is equal to r, which is 2.38 meters, times theta dot, which is 5 radians per second. If we multiply that out, it equals approximately 11.88 meters per second. So that gives us one component of the velocity. We want to find its magnitude, so we also need to find the other component. Looking at this, we sort of have two things that we don't know with only one equation. But the thing that we can sort of take advantage of is our understanding of the geometry of the problem. So we rotate, theta is increasing in the counterclockwise direction. So as we do that, this rotates up, the pin is pushed vertically up the slot. And so we know that our velocity of our pin is straight up. We then also know the component in the transverse direction. So in this direction, it's positive. So it's in the positive transverse direction, and sort of trying to approximate that, the component in the transverse direction is 11.88 meters per second. And while we may not know what the radial component is, we do know its direction. It's along this radial direction. So if we draw a component in that direction, we kind of complete our right triangle. So the transverse and the radial are at right angles to one another. And we have this angle here, theta, which is the same as that angle. It's the angle the vertical makes with the radial direction. And so with this additional sort of geometric information, we can find what the magnitude is. We can find the length of that hypotenuse. That's what we're trying to find. And so again, by geometry, we have this angle theta. We know the opposite side. We want to find the hypotenuse. So again, we use sine SOHCAHTOA. Sine of theta is equal to opposite over hypotenuse. Trying to solve for v. So we multiply the v to the left-hand side. We divide through by the sine. There we have everything what we need. So v theta is 11.88 meters per second approximately. Have sine of 1 radian. We punch that into our calculator, and that works out to be approximately 4.12 meters per second. So that's what we were asked for. We were asked for the magnitude of the velocity of pin A. And so that's what the magnitude of that velocity vector is. So that completes part A of the problem. Going back to the previous slide where we had our expression for the acceleration, that's the next part of the problem that we're going to solve. We can see that one of the things we need is r dot. Okay. So before we move on, we can see that r dot is the radial component of the velocity. So now that we know what this is, or even before we knew what that was, we could also use geometry to find that angle. One thing to notice is that this component is in the negative radial direction. So radial direction is positive away from the reference, away from the origin O. And so this is towards the origin O. So just note it's in the negative ER direction. So again, using geometry, we could use the hypotenuse, but we don't have to. We knew the angle, we knew the opposite side. We wanted to find the adjacent side. We could use tangent. So tangent of theta is opposite over adjacent. We solve for the radial component. We multiply VR to the left-hand side. We divide through by tangent of theta. 11.88 meters per second again, divided by tangent of 1 radian. So that's has a magnitude of 7.63 meters per second approximately. And specifically, if we put it in this equation in terms of direction, it's negative. Okay. And so since VR is equal to r dot, we know that r dot is approximately negative 7.63 meters per second. And just for a sanity check, we can try to determine if the fact that r dot is negative makes sense. So as this rotates up, we can sort of imagine the new position of the arm. You could see that it does indeed, the radius does indeed get smaller as it approaches sort of horizontal. So the fact that the radius is getting smaller matches with what we found here where we had that r dot was negative. So taking that information to the second part of the problem, we need to find the magnitude of the acceleration of pin A. Again, we have the equation for acceleration equals r double dot minus r theta dot squared in the radial direction plus r theta double dot plus 2r dot theta dot in the transverse direction. Again, I'll put in our coordinate frame. Looking at this, right away we can sort of plug some numbers in. So we know that theta dot is 0, so that term goes away. We know what r dot is from the last part of the problem. We know what theta dot is, and so right away we can determine the transverse component of the acceleration. So it's equal to 2 times r dot, which is negative 7.63 meters per second, times theta dot, which is 5 radians per second. We multiply that out. We get that the transverse component of the acceleration is approximately negative 76.3 meters per second squared. Notice that when we multiply these out, we in essence treat radians as a non-unit. So we have that component. We know what r is and we know what theta dot is, but we don't know what r double dot is. So we don't entirely know the radial component of the acceleration. But again, just like we did with velocity, we do have an understanding of the geometry of the problem. Since the pin can only move in this vertical slot, its acceleration must also be vertical. At first glance, it may not be obvious what the direction of the acceleration, whether it's up or down. We sort of know that it's moving up. We know that its velocity is up, but is it moving up at a slower rate or a increasing rate? Maybe you might have a little trouble with that. Looking at the transverse component of the acceleration, we know that it's in the negative e theta direction, so it's going to be down that way. And in order to complete this triangle, the radial component will also have to be sort of down So the total acceleration is vertically downward. And that sort of makes sense if we can sort of imagine what's happening with the pin as this is moving upwards. You might be able to imagine that even though it's moving up, it's moving down at a slower rate. Trying to do a little geometry, we can see that the angle between the vertical and the radial is theta. So if we kind of extended these guys out a little bit, that angle is also theta. You can sort of imagine alternate interior angles or something like that. And so again, we know this side of the triangle. We know the angle, and so we can use geometry to find the hypotenuse, to find the magnitude of the acceleration. So again, we use sine because we have the opposite and we want the hypotenuse. And then in order to solve for the magnitude, we multiply the a to the left, divide through by the sine. Where the transverse component is approximately 76.3 meters per second squared, divided by sine of 1 radian. That works out to be approximately 90.7 meters per second squared. That's the magnitude. If we needed the direction, we would note that it's vertically downward. If for some reason we needed to know what r double dot was, or we needed to know what the radial component of the acceleration was, we could do that from this triangle. But that's all that's asked for, and so that brings this example to conclusion.